Welcome to SciFlux. Here, you get daily coverage of the latest scientific research. Every day, we bring you new research in a clear and simple format so you can stay informed without wasting time. Like the video, subscribe, and leave a comment to stay connected and help this channel grow. And if you want each new research delivered directly to you, join the SciFlux newsletter. Offshore oil rigs tower over the ocean, powering the world while facing extreme hazardous conditions. The oil and gas industry is notoriously risky, with accidents often stemming from unpredictable environments or gaps in safety measures. A recent study analyzed global offshore accident data from 2010 to 2024, applying advanced statistics and a multi-criteria decision-making model to identify and rank hazards by severity and likelihood. Researchers also explored how different risks interact and proposed strategies to mitigate them. The outcome goes beyond numbers. It provides a practical blueprint for safety. By highlighting the most critical dangers, operators and regulators can shift from reactive responses to predictive, proactive safety management. In an industry where every decision can save lives, understanding these risks is essential to building a safer offshore future. Moving forward, gallium nitride, GaN, is redefining power electronics, smaller, faster, and far more efficient, powering everything from phone chargers to electric vehicles. Yet even this superstar faces a challenge: dynamic on resistance, or R sub-on. When a GaN transistor switches on, its resistance can spike unexpectedly, generating heat and wasting energy. This effect is amplified in advanced chips, like GaN-on-Si monolithic half bridges, where tightly packed components trigger a backgating effect. Traditional measurement methods often miss this, leaving engineers with an incomplete picture. To tackle the issue, researchers developed a method to measure dynamic R sub-on under real operating conditions, capturing the hard switching these devices actually encounter. The findings were striking. Actual resistance was nearly double previous estimates. Tests with buck converters confirmed that monolithic GaN devices lose efficiency under real-world stress, demonstrating the significant impact of backgating and hard switching. This advancement equips engineers with a precise, practical way to evaluate GaN power devices, ensuring the next generation of electronics is not only powerful, but reliably efficient. Next, imagine a future where renewable energy flows seamlessly across continents, powered by high-efficiency DC grids. But with great electricity comes great risk, and protecting these grids requires advanced circuit breakers, particularly hybrid MVDC breakers using asymmetric IGCT semiconductors. These IGCTs face a hidden danger: sudden reverse voltage stress, especially when a freewheeling diode is conducting. Left unchecked, this stress can damage the device and threaten grid stability. To address the issue, researchers developed a detailed circuit model incorporating real-world factors like parasitic inductance and gate protection circuits. Their findings revealed two critical solutions: minimizing parasitic inductance in the diode branch and deactivating the IGCT gate unit's overcurrent protection. Together, these measures significantly reduce reverse voltage stress. The outcome is a more reliable, safer hybrid MVDC breaker, capable of supporting stronger and more resilient DC grids. By mastering these precise technical details, engineers can transmit renewable energy farther and smarter, keeping the lights on while driving a sustainable future. Moving forward, imagine a world where every joint replacement or bone scaffold is designed specifically for you, fitting perfectly and restoring function with unmatched precision. In orthopedic surgery, this vision is becoming reality through personalized medicine. Traditional implants often follow a one-size-fits-many model, which can compromise fit and long-term outcomes. Additive manufacturing, or 3D printing, is now transforming this landscape. A recent review highlights how 3D printing enables surgeons to create implants tailored to each patient's unique anatomy, using biocompatible materials and precise design techniques. This approach enhances fit, function, recovery, and cost efficiency, while also accelerating production timelines. Challenges remain, including regulatory hurdles, material limitations, and ethical considerations. The promise is clear. Personalized, 3D printed orthopedic solutions can reduce complications, speed recovery, and improve quality of life. As the technology continues to advance, surgery is evolving from mere repair to truly customized restoration, crafted just for the individual patient. Next, consider the challenges of high-speed machining, an essential process across multiple industries. The relentless friction and wear at the cutting tool's edge constantly degrade both tools and machined parts, affecting lifespan and product quality. To tackle this, researchers investigated the extreme contact conditions faced by cemented carbide tools when cutting titanium alloys. By simulating intense tool-workpiece interactions, they tested titanium samples under a wide range of pressures and sliding speeds, from conventional pin-on-disc experiments to high-velocity gas gun tests, carefully measuring friction and analyzing wear patterns. Their results revealed a nuanced picture. At high pressures and low speeds, adhesive forces dominated wear, while at higher speeds, tribo-oxidative and abrasive mechanisms became the main drivers. Importantly, friction did not increase linearly with pressure and velocity, highlighting a complex interplay of forces. These insights into friction and wear under extreme conditions are critical for designing longer-lasting tools and optimizing machining processes, ultimately improving precision, efficiency, and durability in demanding industrial applications. Now, envision a construction sector where every material, drawing, and payment is tracked with full transparency. This is the value blockchain could bring. But bringing this technology into the Jordanian construction industry introduces substantial challenges. Researchers mapped these obstacles through a structured process, first identifying issues via bibliometric analysis, then grouping them under the PESTEL framework: political, economic, sociocultural, technological, environmental, and legal, and finally surveying local construction professionals to rank their importance. The results were clear. The toughest barriers are technological. Weak IT infrastructure, data validation, and privacy concerns, scalability limitations, and hesitation toward adopting new digital tools were the most significant constraints. By applying the PESTEL method, in this context, the study systematically outlined 16 core challenges and delivered actionable insight to help the sector move toward a more secure, efficient, and digitally enabled future. Next, hybrid manufacturing holds strong potential, but powder-based processes and their support structures often limit efficiency. A new wire-based directed energy deposition approach addresses this gap directly. Using an 8-axis robotic setup and a non-parallel slicing strategy on a turn-tilt table, the process can build complex overhangs without any support material or powder waste. The team validated the method by producing demonstrator parts, confirming high stability and repeatability. This advancement marks a meaningful step toward more efficient, flexible metal additive manufacturing, reducing waste while expanding design freedom. On another research, engineers are pushing to model soft materials with higher accuracy, especially platinum-cured silicone used in robotics and medical prosthetics. This study tackled that challenge by running uniaxial tensile tests, fitting the results to several hyperelastic models in MATLAB, and validating the behavior through ANSYS simulations. The Mooney-Rivlin model delivered the strongest fit, but early simulations fell short because they assumed the material was fully incompressible. Once compressibility was introduced, the results aligned. A Poisson's ratio of 0.41 produced near-perfect agreement between experiment and simulation. The outcome is a more reliable framework for predicting silicone's nonlinear elasticity, enabling better product design and more realistic performance in next-generation medical and soft robotic applications. Last one for today. Carbon fiber reinforced polymers offer outstanding strength-to-weight performance, but grinding them is risky. Heat buildup can quickly damage the material, especially when temperatures surpass the glass transition point. The problem becomes even more complex because fiber orientation dramatically shifts how cfrp reacts thermally under identical machining conditions. Researchers tackled this by building a universal, process-independent model using spatial fiber cutting and engagement angles, allowing a controlled study of temperature behavior across all possible engagement scenarios. With a thermographic setup, they captured precise temperature data while testing different abrasive materials, corundum and diamond, and a range of cutting speeds. The results deliver a clearer understanding of how grinding parameters drive thermal loads and material damage. This framework creates a practical path to optimize grinding strategies, protect component integrity, and elevate the manufacturing quality of advanced cfrp structures. Last one for today. Thanks for watching. If you enjoyed the video, please like, comment, and subscribe. Also, join our newsletter to stay informed with the latest discoveries shaping science and innovation. See you tomorrow with a new round of breakthroughs. Take care.